Before we leave this section, I'd like to kind of leave off where we started off. We had been talking about the different types of bonding and being able to identify whether or not a compound would have ionic bonding or covalent bonding. And I know the major focus of this chapter was really focusing in on ion formation and ionic bonding. But again, I want to be able to compare and contrast the properties of compounds that would have ionic bonding versus covalent bonding. Now, before we get started here, when we're talking physical properties, we're talking about watching things on our macroscopic scale, like on the size of like we are people. But in order to understand the why, we need to shrink ourselves down to the microscopic and understand the interactions of matter at that very tiny, infinitesimally small level. So first, I want to start off by looking at an ionic compound. This is what a typical ionic compound is going to look like, still at that macroscopic scale, but zoomed out just a tiny little bit. This looks like pretty much a hot mess, an organized hot mess, but still a hot mess. We call this structure that you're seeing in front of you a crystal lattice. And a crystal lattice has a very intricate set of organization on the inside of it. Now, what I want you to imagine is that in an ionic compound, such as sodium and chlorine, sodium chloride, when those two atoms or ions come together, they come together in a defined ratio, 1 Na to 1 Cl. But if an NaCl combo sits next to each other, sometimes the Cl gets a little confused. It forgets which Na is actually belonging to it. Now remember, it has a full negative charge, so it's going to be attracted to anything positive. And the same thing can go for that positive Na. Sometimes it gets a little confused and forgets which Cl is actually belonging to it. It's positively charged, so it's going to be attracted to anything negative. So what you see when you have an ionic compound is that typically they tend to kind of coagulate, aggregate all together like this in this beautiful organized schmishmash called a crystal lattice, where every positive ion is completely surrounded by negative ions, and every negative ion is completely surrounded by positive ions. And depending on the combination and charges of those ions, you can get some really cool crystal shapes. Take a look at NaCl, the larger shape down below. If you've ever actually shaken out a little bit of salt and held it in your hand and took a really close look at those salt crystals, you'll notice that they're kind of a square or cubic shape. And that has to do with how the ions themselves are actually sitting together, because that pattern repeats and repeats over and over again until it gets large enough that you can actually see it and hold it in your hand. And I think that's pretty neat. All the way down to the atomic level, you're seeing what it looks like on our large human level. Now, more than that, I actually want to take a look at what this crystal lattice looks like when we expose it to some heat and some temperature. Now, you may remember that when we're talking about temperature, we're talking about the average kinetic energy of the particles. So if I increase the heat, if I increase that temperature, I should see the particles be able to move faster. That's what kinetic energy is all about. Now notice what happens to these molecules, or I should say atoms, that are stuck on the inside of this crystal lattice. Remember that they are all held together by ionic bonds. So here we go. Let's heat up this structure. So here we go. Here's just a little zoom in of the sodium chloride structure. And we're going to slowly increase the heat. I know we're kind of zooming around a little bit here. Notice that all of a sudden the atoms start to vibrate a little bit more aggressively. I keep ramping up that heat, and again, they vibrate more and more and more aggressively, constantly stressing that bond until finally they break the bond and they're able to move into the liquid phase now, and the atoms start to slip past each other. Now, in order for that ionic structure to melt, you have to break the ionic bonds. Bonds store a lot of energy, so it takes a tremendous input of energy in order to break apart an ionic structure like that. Now, let's kind of compare and contrast that with a covalent compound. Now, you may be wondering, well, this doesn't look too terribly different. This also looks like a crystal lattice. And in fact, you'd actually be correct. This is a crystal lattice. Covalent compounds are capable of forming them as well, but we were going to call them instead a networked covalent solid. And that's actually a pretty important difference, which I'll explain here in just a moment. Now, before we do, just like how NaCl's repeated structure makes it look like this cubic structure out in the real world, so do covalent compounds. Now, one covalent compound that you might be very familiar with is good old H2O, which is actually what you're seeing here on the screen. And I'm not sure if you can see it or not, but there's a number of these little connecting bars that are holding all of these molecules together. You should see about 6-ish of them. Well, here's H2O, and it's in a networked covalent solid. You might better know these as snowflakes. Notice how many sides they have. Interesting, 6. And that's because it's making those 6 interactions that we get these beautiful 6-sided snowflakes. Again, what's happening all the way down at that microscopic level is determining and showing us what's going to happen in our macroscopic world. And that's part of the reason we learn chemistry, is to understand better the world around us. So again, it's really kind of cool that this 6-sided structure all the way down to that microscopic level determines this 6-sided structure in real life. Now, I want you to kind of compare and contrast that with what you just saw. This is a cup of ice. Now, this is a covalently bonded compound in its networked lattice. I'm going to expose this to some heat. I want to see what happens over time. So notice I'm going to start to slowly ramp up the heat here. Notice that the molecules themselves are starting to vibrate and our solid has melted, breaking all of those little bars that were holding them apart before. But what do you notice here? The molecules themselves have stayed together. There's still 2 H's bonded to 1 O. We did not see that in the ionic compound. The Na and the Cl completely broke apart, but here the H's and the O's are still connected. They're just moving faster and faster and faster as I continue to increase that heat. So again, taking a look back at this lovely crystal lattice, or I should say networked covalent lattice for water, 2 important things that I need to show you. Number 1, these black bars here. You'll notice that they're always there combining 1 oxygen with 2 hydrogens, making water. Those forces are covalent bonds. They're very strong. And then we also have a secondary layer here. So we have here 3 separate water molecules, and you see these little lines that are connecting them. Those little lines are something completely different. Those are not bonds. Those are something that we call intermolecular forces. Those are forces that hold molecules together. We will be learning about them in the next chapter, but I thought you might like a little bit of a sneak preview here and now. Now, intermolecular forces are not as strong as true bonds. True bonds are always going to be stronger than intermolecular forces. Now that we know a little bit more of this background, it might be helpful to apply it to why we see certain things in the real world. So, melting. During the process of melting, in an ionic solid, it is important to remember that in order for that solid to melt, I actually have to break a bond. We call that amount of energy that it takes to break those bonds lattice energy, because that's how much energy it takes to break apart its crystal lattice. Now, in a covalent solid, we don't actually have to break any bonds. We have to break intermolecular forces. Those are the forces that hold molecules together. Now, they're weaker than bonds, so it typically doesn't take as much energy. So what will tend to melt first, if you're in a little bit of a contest, are your covalent solids. So you'll notice that your covalent solids tend to have very low melting points. Now down at the bottom, I just put up here a little bit of a ranking system for you. Your strongest forces all the way down to your weakest forces. Again, your strongest force that we know is going to be an ionic bond. Your weakest force is going to be an intermolecular force, the forces that hold molecules, covalent molecules together. So ionic solids will tend to have high melting points because it takes a lot of energy to actually break those true bonds, whereas covalent solids tend to take a little bit of energy, lower melting points, the point at which it actually is going to melt, the temperature at which it's going to melt, low amount of energy because we're breaking intermolecular forces instead. Something else we can discuss is solubility. Now, solubility means to dissolve in water, or its ability to be soluble or dissolve in water. And again, at this point, we don't necessarily have a specific rule to tell the difference between an ionic and a covalent part. We're going to learn about them in subsequent learning, but not right now. So again, just kind of know that at this point, you can't simply tell an ionic and a covalent substance apart by chucking it in water and seeing whether or not it's going to dissolve. However, there is something else you need to know: conductivity. Conductivity is the ability to conduct electricity. And you can kind of see here this electrical bolt going through this liquid solution. We always test these things in water because the items have to be able to dissolve in order to conduct that electricity. In an ionic solid, when we break up that ionic solid, we actually have to physically break a bond in order to get those particles apart from each other and to get them to dissolve into water. Which means that we actually have two separate ions, or things that have charges. Charges are able to conduct electricity through solution. No charge, no conduction. So any ionic solid that's able to dissolve will conduct electricity. But if it can't dissolve, then the ions stay stuck together and they do not conduct. Now, covalent compounds, in order to get them to melt, we're breaking intermolecular forces, not bonds. There's no charges involved there. No charge, no conductivity. So again, to summarize here, in order to get it to conduct electricity, it has to be able to dissolve. Ionic solids, sometimes they can dissolve and sometimes they don't. We're going to learn about how we can predict that in a little bit. But if it does dissolve, the bond is broken, the ions are separated from one another, and it can conduct electricity. No dissolving, no conduction. Covalent compounds can dissolve, but they're not breaking bonds when they do. No charge, no conduction.